Great. So welcome back, everyone, to the last day of our workshop on transport fluid and mixing. Sorry. And the first speaker today is Michele Coti Zelati from Imperial College in London. He's going to talk about the exponential mixing for random flows. Please, Michele.
Yeah, thank you very much, Gianluca, and the organizers for the invitation. Thank you all for being here. Yeah, so I will talk about exponential mixing for random flows. So this is a topic that has been touched upon by a couple of speakers this week, and I'll just give essentially my point of view on the subject. And what I'm going to say today is joint work with Alex Blumenthal in Georgia Tech and Richard Garbani in Leipzig. So, okay. Yes, I mean, I will talk about passive scalars, and some of the concepts from the first bullet point here have been discussed already, so maybe I won't spend too much time. And then, yes, I will try to tell you how to get chaos for certain dynamical systems driven by randomness. And then I will talk about exponential mixing and how to get smooth exponential mixers on the two torus, basically. So, okay, so the problem that I will look at is a problem of passive scalar rho that is advected by an incompressible velocity field u that can be time dependent and space dependent. Of course, I will think of it as being given and divergence free. And the setting will be the simplest possible setting, which means periodic box in dimension d. And I will consider only mean-free solutions. This is a property that is propagated by the flow, and so I can just assign it to the initial datum, and this will be fine for all t. So the idea is to study the long dynamics of this equation, and there is one only possible thing that can happen in many situations I will describe, that is rho converges to 0, so to its average. Okay, and essentially the averaging mechanism is what sort of drives all these mixing problems. So if you look at the case of a shear flow, say on a two-dimensional periodic box, the equation looks like this. And if you look at the simulation, this I did it for u of y equals sine of y. You see that if I start with an initial datum that is a concentration that is more or less 1 here and minus 1 here, so 0 average, then you see exactly these smaller and smaller spatial scales appearing. But you also see that the x average, so if you look at the horizontal lines, is a conserved thing. And this can be seen just from the equation, because you just integrate the equation in x, and by periodicity this term drops because the velocity field doesn't depend on y. So of course you cannot think of mixing everything every initial datum, say in L2. So if you were here at the Andre's Lazier talk, we talked about universal mixers. Of course, shear flows cannot do that, but for just this reason, right? That you have a conserved quantity. But if you start with the initial datum that has no x average, then you may guess that there is some averaging in the y direction. And what usually averaging is associated to weak convergence to 0. So what you could think of is that rho minus the part that doesn't change goes to 0 weakly as time goes on, right? And this is, you know, a weak definition of mixing, if you like, but it's a natural one, and it applies to many problems. In fact, if you think about kinetic problems and so on, usually there is some average quantities that do converge somewhere, and the sort of mechanism is similar to this. You can also try to mix more general initial data, and this is something that I took from the website of Van Nest from Edinburgh. So this is mixing by obviously a more complicated flow, and you have an initial datum with high concentration and low concentration, and you steer it in a disk by random flows, okay? And well, I don't know exactly with what velocity field it has been done, but it's been done with a random flow that is supposed to be chaotic, okay? And so you see that right away, all the initial data, in particular this one, doesn't have to be mean zero in a direction, but of course, it will be mean zero in the whole domain, is advected very fast, and you have these smaller and smaller spatial scales appear. And in this picture, in fact, you see also the effect of a small diffusion parameter. I won't talk about all this effect at all, but you can understand it that it's there from the picture because you see some blurring of the, let's say, of the level sets of the initial data. Okay, it's not just transported, that there is some diffusion, but on a short time scale, mixing is the prevalent effect. And so really, you see this information traveling to smaller and smaller spatial scales. And so questions that are natural are, how can I measure how mixed is the scalar at any given time, and how fast is the scalar mixed, okay? So we saw already that to understand this sort of weak convergence to zero, this cascading process in which information travels to smaller and smaller spatial scales, the negative sublevel norms are a good tool, okay? And if you think about it, yeah, convergence to zero of negative sublevel norms for, let's say, functions that have L2 norm fixed is equivalent to weak convergence, okay? So precisely, we can decide that mixing is quantified by an H minus S norm, and mixing means that this quantity goes to zero as t goes to infinity. The S parameter here is not so important mathematically in general, but for example, if you're in 2D and you want to measure an average length scale of the solution, it's been argued that S equal 1, so the H minus 1 norm is the correct quantity just by dimensional analysis. It has dimensions of length. Okay, but in fact, Andre made an argument in which S equal 1/2 is also, not Andre talked about an argument made before, in which S equal 1/2 is a good measure of mixing as well. It doesn't really matter from my point of view, okay? However, this is not, this is the notion of mixing I will use, but for what I'm going to see later, I want to just think of this quantification of mixing in a different way. So we know that, well, the problem is very much related of studying the behavior of rho is very much related with the characteristics of the equation. So if we just look at the motion of a particle that starts at the location x, then xt of x describes the position at time t of the particle, right? And this just goes around with the velocity field that I'm giving. And very much related to the decay of the H minus S norm is the so-called decay of correlation. So decay of correlation is looking at this type of integrals, f composed with the flow, capital X times g, does it go to zero or not? And because X is measure preserving, I can also phrase it in terms of this quantity here with the X inverse. So if you think about it, this is exactly the solution of my transport equation that starts at time equal to zero. It starts at initial datum g, okay? So, and if you think about the H minus S as being defined by duality instead of Fourier series, right? This is exactly, and if you think of f being an HS function, and also say g maybe to be an HS function, this is really trying to understand what the H minus S solution, the H minus S norm of rho is, rho starting at the initial data. So the point is that if I can quantify these in terms of the HS norm of F and the HS norm of G, then I will be able to say something about the H minus S. And this is a more, say, dynamical system point of view, but that's what I'm going to try to talk about today. So that's what I want. So in terms of quantifying this mixing effect, let us think about the H-1 norm, and I just state a few results. I'm trying to name everybody in this conference, but sorry if I missed someone. But so if you think about shear flows, so the example that I told you before, well, it turns out that the rate of decay of the H-1 norm only depends on the nature of critical points of the shear that you have. So in particular, if you think about, so n here is the maximal order of critical points. So how many derivatives vanish? So n-1 is the maximal number of derivatives that vanish at critical points, basically. So if you look at sine of y, n is equal to 2 because there are critical points in which the first derivative vanishes, but the second derivative will not vanish. Okay, so n equal to 2. So you see that the flatter the critical points are of a flow, the slower the mixing. Okay, so if n is larger, this rate is lower. And you can do this for circular flows, and you get similar rates here depending on the nature of the flow. And this was done by Gianluca, Renato, and Christian, and also by myself and Matthias and Tarek. And the idea is that you can sort of think of this as sort of an oscillatory integral. So it really looks like averaging in a sense. And that's how you prove by a sort of stationary phase type argument. So if you drift away from the smooth case, what happens to not very smooth shear flows? And there is sort of this idea that rougher velocity field, in fact, mix faster. And however, with Maria and Klaus, we looked at the C alpha shear flow that's like a Weierstrass function, and it's C alpha at every point. And the mixing rate is still 1/t, okay, in the 2D periodic setting. However, it was proven by Lucio Galeatti and Gubinelli that generically you expect that the rougher the field, the faster the mixing. So if alpha is smaller, so the shear flow is rougher, then the mixing is faster. Okay, so this is generically in the sense that the set of C alpha shear flows that don't mix at this rate is measure 0 in some sense. However, the only example that I know, at least, is this example that we have that doesn't make this fast. So I don't know how to construct an example, an explicit example that mixes that fast. Of course, if you're just restricting yourself to autonomous velocity fields, you cannot mix faster than 1/t. And we heard about this result earlier in the week. But if you go to more complicated flows, in particular time-dependent flows, then they can be exponential mixers. So this rate can be e to the minus lambda t for some lambda. In this construction, they were initial data dependent, and then in this construction of Elgindi and Zlatosh, it was instead made basically initial datum independent. And exponential is the best possible rate that you can get. Okay. For smooth flows and so on. I'm talking about the nice settings. Okay, so this is deterministic result. If you look at probabilistic results, then was this paper of Jacob Drossen, Alex Bloomington, and Sam Push-Smith, in which they proved that if you take U as the solution of the stochastic Navier-Stokes forced by additive noise, then you do get exponential mixing, okay? And this is a universal exponential mixer. I think this is a really amazing work, in fact. And On the other side, if you assign some specific properties to your velocity field U, like Gaussian and decorrelated in time, and the most well-known example is the so-called Cracknell model, you also can get almost sure exponential mixing in terms of, and lambda is some rate, okay? And this was done by Flandoli, Galeatti, and Lu, and by Guess and Yaroslav last year. But as Andreas Latos, for example, mentioned in his talk, there is an open question in this business, which is, can you find a possibly time periodic smooth universal exponential mixing on the torus? And by smooth, I mean C infinity in space and C infinity in time, but also L infinity in time, so uniformly bounded in time. Okay, so this is a question that has been open for a while. In these cases, the thing is that these are not really L infinity in time, and they are not also C infinity in time. What you can do in this case, you can make them CK in time for any K, for example. But still, you will have some excursions that will. So you won't get the L infinity. In this case, you have to adjust the noise, and so I think some subset of this group is working on something like that, in a sense. But they are smooth in time, in space. That's not a problem. Okay, so what I want to look at is an example of Pierre Lambert in '94 that was mentioned already, and in which the velocity field U just alternates between, let's say, two shear flows, okay? So every time tau, okay, I alternate between a horizontal and a vertical shear. And what I do, I also randomize the phase of the shear flows. So basically at time, say, from time 0 to time tau, I shear with sine of x2 minus omega 1n, where omega 1n is the time, in the first interval of time. So for n equal 1, I have the first component of my 2 vector omega of random phases. And the same for the vertical shearing. So at the time from, say, time tau to time 2 tau, I shear vertically with the random phase omega 2n, okay, or omega 2 1, if you like. So superscripts are just the components of the vector of random phases, and subscripts are the time in which I'm doing this. And this has been used a lot for simulations of exponential mixers. And it's a very simple example and very explicit. What was mentioned earlier in the week was an example similar to this, in which instead of sine, you would have a wedge type thing. And this is a smoother version of that, in a sense. So this is a good candidate for exponential mixing, and that there's been a lot of numerical evidence. And what I want to show you is that this is indeed an exponential mixer. Okay, so I want to rephrase this a little bit as a random dynamical system. So I'm just redefining my functions f, h, and fv as the basically velocity field. So where does my particle go after each shearing? Okay, if I horizontal shear, well, I move the first coordinate by this amount, okay, where beta is my random phase. Or if I vertically shear, I move my point x1, x2 to this location, okay? And of course, I can write down the position of my particle at time 2 tau. Remember, I shear for time tau horizontally, tau time vertically, and by composition of these two, okay? So here, omega 1 is the vector of omega 1, 2, and omega 1, and I compose the horizontal and the vertical shear, okay? So just to fix some notation, I'm going to need the whole sequence of possible random shifts that I denote by underline omega. Okay, this is just a sequence of two vectors, okay, chosen 0 to pi because it's just a frequency. And I can write, of course, the position of my particle at time 2 tau n in this way, but just by composing these f's every time I change the phase, okay? So every time I have omega 1, omega 2, omega n. So here I'm a little bit abusing notation in the sense that of fn of omega doesn't depend on the whole sequence, but just depends on the first n elements of the sequence. But I just didn't want to put n's everywhere, subscript, superscript. So I think I hope this is clear enough. In fact, there is a nice argument by Zlatosh in their mixing paper that this is enough to look at this type of dynamics to actually get the full time continuous dynamics. So what I'm going to do now is look at the discrete dynamics and try to understand how to prove exponential mixing for this type of compositions on maps. Okay, so just to do it in a bit of a more general way, you know, one can fix a probability space omega 0 and a complete matrix space. So this is the phase space in which my dynamical systems live, and this is related to the type of noise I'm choosing, and the type of noise that I'm choosing is going to be sequences where each sample is going to be taken in this omega 0, and then I just do it n times, and I just look at compositions like this. And I want to see this really as a Markov chain, so I can define the kernels in this way, the transition kernels that can define for every n by this formula. So in the case of Pierre Lambert, really is x is be the 2 torus, okay, and P0 is absolutely continuous with respect to the back measure, and f omega is measure preserving because I have a divergence-free velocity field. So, and the whole what I'm gonna say after this essentially holds in this case. So X just needs to be a compact manifold, finite dimensional compact manifold. P0 has to be absolutely continuous with respect to the back. It's not really needed that you have measured preservation, but let's say that for the conclusion C, so I'll just assume it from the beginning. Okay, so there are important properties of random dynamical systems that we should take into account. So one of them is irreducibility. So irreducibility means that there are no disconnected places in the phase space. Okay, so every if I start from any x, I can reach any u in n iterations. Okay, so that's one important concept. Aperiodicity, I don't want to allow cyclic behavior. Okay, so in fact, I need a bit of a stronger version of this, which is called stronger periodicity, but let's not go into that. And some regularity. So usually it's assumed that these Markov semigroups are strong Feller, which means that given a test function phi, or an observable, actually phi, that is just bounded and measurable, then P of phi is continuous. And if you think about it, this is really an effect of randomness, right? If you think phi to be the indicator function of a set, for example, well, at time 0, you either are in the set or not. And at time 1, this is saying that it's not really, it's not a sharp, right? It's not, there is a smoothing for which, okay, you may, there's not just probability 1 or 0 to be in the set or not. Okay. However, it turns out that this may be strong, too strong for some of the chains, Markov chains that I will consider later. So there is a weakening of this property that's called a T chain that doesn't necessarily assume that the kernel is absolutely continuous with respect to the reference measure, say the back measure, but it also ensures it's not completely singular. Okay. So, and in fact, if you have a finite state Markov chain, these three properties already tell you something very important about your Markov chains, that you have a unique ergodic invariant measure, and it gives you also a explicit convergence to equilibrium. So to the measure. However, you may need an additional properties depending on the setting of your problem, and so I'll tell you. I'll just list the last property is this drift condition property. That is the existence of a so-called Lyapunov function of V, for which, well, this inequality holds. So this condition is only really needed if you work in a space that is not compact. In a compact space, this condition, you can just take V equal 1 and C be the whole space, and this is not a problem, okay? So, so this is something that will be useful later. But all these basically properties of the dynamical systems tell us something about ergodicity of the Markov chain. So this is usually known as Harry's theorem. So if you have something, a FLIRT transition kernel that is a T-chain, is topologically reducible, is aperiodic, and satisfies the drift condition, then you have so-called V uniform ergodicity. There exists a unique invariant measure, phi, such that this invariant measure attracts all possible observable at a rate that is exponential. However, this is not really uniform in all phase space, but is D uniform, okay? So you have this type of, the Lyapunov functional comes out here, and in this norm, the norm V is simply the norm of the absolute value of F divided by V, okay? So it's a null infinity type norm weighted by V, okay? And as I said, if you look at the one-point process for the Pierre-Ambert problem, you don't need to construct a Lyapunov functional, but this theorem is just applied with V equal to 1, okay? So that is uniformly geometrically ergodic, and this is not too hard to prove, okay? So once you have this, you can start trying to understand what are the chaotic properties of your Markov chain, and in this case, what is the chaotic properties of the Lagrangian flow of our flow, of our velocity field. So essentially, what you would like to try to understand is whether this process has a positive Lyapunov exponent. So the fact that you have a Lyapunov exponent, meaning that you have this limit existing, is something pretty standard in ergodic theory, and it holds for these cases. Okay, so in the case of Pierre-Ambert, you can prove that, well, this lambda 1 exists and it's constant, so it's not a random thing, it's just a deterministic number. Okay, for almost every sample path or noise path and every initial condition. Okay, so this should describe the infinitesimal rate of separation of 2 points that evolve under the flow that you're considering, and this is exponential separation, in fact. Knowing that this lambda 1 is positive, it really tells you that, okay, yeah, it does separate, and there is a way to check whether it's positive or not. That's called usually Furstenberg criteria. So I want to write it here because I want to give you some insight about this criterion and how we check this for Pierre-Ambert. Okay, so here I'm just introducing some notation that, but it's not really anything mysterious. I just want to see my composition of functions as a function of the noise only for a fixed initial condition x. Okay, so this phi of x takes values in the n copies of my base probability space omega 0, and I just look at this composition. And what I have to check for this composition is that if I differentiate these with respect to the noise path at some time n, then this should be surjective, this matrix. And the restriction of the Jacobian with respect to x n with respect to the noise path to the kernel of the derivative with respect to the noise is also surjective as a linear operator. Okay, so it sounds hard, but in the end, this is just checking that some matrices have full rank or not. Okay, so if you want to just trivialize these conditions, and so if you could do this, well, then you have that the Lyapunov exponent is positive. Okay, so what does this mean for our Pierre-Imbert model? So I just tried to rewrite it here. So at each instance of time, you have 2n degrees of freedom in terms of noise, because at each instance of time, you have two phases, right? And so every time you want to compute the Jacobian with respect to this, well, you have always two rows, let's say, given by the two components of phi, but you have 2n columns, okay, where n is the time iteration. And you can do this in general. I'll come back to this later, but let's focus on this. So, and what is the kernel of this matrix? Well, I mean, this depends on your choice of x star and omega star. However, because I need condition 1 that tells me that this matrix is surjective, the kernel is 2m minus 2 dimensional. Okay, the rank is 2 of this matrix, so the kernel is just 2n minus 2. And what is the tangent space of SL2? Is just the space of matrices that have 0 trace. So this is 3-dimensional. Okay, so you want to now take this Jacobian, restrict it to the kernel, and be surjective. Okay, so how many iterations that do you have to do? Well, you need that the kernel, so the base space, is at least 3-dimensional. Okay, otherwise you will never get something surjective. And this tells us that n has to be greater than or equal to 5/2, so n equals 3 in this case, right? So what you have to do to check this theorem is that you have to compose the map 3 times of Pierre-Imbert, take the Jacobian with respect to the 6 noise parameters that you have, because you have 2 each phase, and then hoping that that's full rank. And this can be just checked by computer. So that's hard to do it by hand. I strongly discourage you to try to do it, even for 3 iterations. But you can check by computer, and this is rigorous. It's just something that can be done rigorously by computer. Okay. Of course, if you just do this in general, this is just to give you a flavor of how costly this can be. Well, you can think of having at each instance of time an L-dimensional noise parameter and in a D-dimensional problem. Okay, so instead of T2, you have TD. You do your computation and you get that n has to be bigger than d squared plus d minus 1 over L. Okay, this is a necessary condition. You still have to check that the matrix is full rank, but you see this n increases with dimension, and also it increases if you decrease the amount of randomness in the system. Okay, this is a well-known fact, in fact, in all this business, but this is also nicely explicitly put here. So, in fact, you could try to do it with less phases or more phases or something like that. And I'll tell you how to put more randomness if you're Lazier and you want to check only, say, n equal 2, for example. So, but the theorem is that if you take the Pierre-Imbert model with the 2 different random phases, okay, at each half-time step, right, then you have a positive Lyapunov. So you don't, in fact, have to change phases. You can just take a sine of x minus omega 1 and then sine of y minus omega 1 in the next iteration. So keep the phase fixed, but you're going to change it at the next at n equal 2. Okay. So, but for n equal 1, you keep the same. You can do it, but you see from here that basically instead of n greater than 5 over 2 becomes n greater than 5. So you have to take, you know, the Jacobian is much bigger. Okay, so you have to take 5 iterations of your map, and you know, it becomes a bit of a mess. Of course, you can try to do it instead of with fixed phases. You can and randomizing the switching times. Okay, so you can shear horizontally for time tau 1, and then vertically for time 1, 2. This introduces again 2 degrees of freedom in terms of randomness, or keep the same switching time, but you change it at every iteration. So this works as well. There is no need of using the function sine, although you cannot really do the wedge, like the non-smooth wedge, because we assume that f is like C2 or something like that. So this needs a bit of regularity. And of course, but I mean, this shows a bit the robustness of this type of framework, except that you do need some randomness. So I think it's fair to say that it's a completely open question whether Lyapunov exponent is positive when you have no randomness in the case of Theorem. Okay, so I want to just go to the exponential mixing now. So in fact, what we can prove is that not only you have chaos, so positive Lyapunov exponent, but you do have exponential decay of correlation in the Pyramid model. Okay, so exponential decay tells me that, okay, if I look at these correlations, decay of correlation quantity between phi and psi, this decays exponentially fast, and I can quantify the dependence on phi and psi in terms of HS norms of these functions. And here it's all mean-free functions, so it's really H dot, but okay, I don't care. And you have a random constant in front of here that has some moment bound. Okay, so we can prove this as well, and let me just give you a flavor of what it takes to prove such a result. Okay, so it's not enough to just study the Lagrangian flow. That's what I want to really emphasize. So if you look at the correlation between phi and psi, that is defined exactly by what I want to prove that exponentially decays, and you try to estimate the probability where this is big, right? You can just use Chebyshev inequality and reduce it to understanding the decay of this expectation. Okay. So in particular, if you think epsilon to be, say, e to the minus gamma n, then this becomes e to the plus 2 gamma n, and you want to be able to make this decay faster than e to the 2 gamma n. But gamma can be arbitrarily small, so I can try to play with that. And if I rewrite this square by sort of introducing a dummy variable y, okay, you can see that this does not only depend on the 1-point process, but it really depends on the 2-point process. So a joint process that take a point x0, y0 to xn, yn by, you know, iterating the map, my original map, on the product space x cross x. And so if you define exactly the 2-point process as the Markov kernel associated to this dynamical system, then, you can phrase sort of the decay correlation in terms of this 2-point process. So if you can prove that the 2-point process is geometrically ergodic, then you win, okay? So the only problem with this is that you do have an invariant measure that is the product measure Lebesgue, if you like, or pi cross pi, where pi is the invariant measure of the 1-point process, but it is not the only one you have. So you cannot hope to just have uniform ergodicity because the diagonal is invariant under devolution. Okay, so I explained this here. So if, in fact, you start from the diagonal, so instead of xy, you have xx, you stay in the diagonal. There is no question about that. And so you have to consider this process on a non-compact space. So it's, say, torus cross torus minus the diagonal, okay? And that's where the abstract heuristic theorem in its full glory comes into play. Okay, you do need to construct a Lyapunov function of V. Okay, you cannot just apply that anymore. So this Lyapunov functional that you have to construct should blow up on the diagonal. Okay, so it's you know, it's an educated guess to just think of this V as distance between x and y to some power minus p times a psi that is some correction that it doesn't affect the values near the diagonal. So psi, in fact, should be bounded below in a neighborhood of the diagonal, okay? And have some other properties. So how do we construct such a thing? I'm not going to show you the whole construction. I think Jacob yesterday talked a little bit about something similar, but I just want to tell you that, again, you have to study a further process, okay? So, because essentially what you can think of is that, okay, if I'm very close to the diagonal, then the values of V only really depend on the values near the diagonal delta, okay? So instead of considering the two-point process, which may be complicated, you can try to linearize the two-point process by the one-point process and the Jacobian. And the Jacobian takes, say, vector V's that are just directions, okay? You don't have to, so this, you have to look at the direction, because you can think about it like this. You have a process that you may have a stable manifold that drags you to the diagonal and a stable manifold that repels you from the diagonal. And you really just want to understand in which direction you're going, and if this direction does attract you or not to the diagonal. And if it does, well, that's when the Lyapunov function comes into play, and you know the Lyapunov function will become big if you're near the diagonal. So this is all to say that there is a further process that you have to study that is called the projective process. Okay, and this is the one-point process, and let's say the process that is the Jacobian normalized to have norm 1. So this is a process that takes value in T2 cross some sphere, depending on where what the dimension of your problem is. Okay, so I think I'm close to finish. So let me just tell you that we do write a checklist for what you have to do to prove exponential mixing for this type of dynamical system. So you have to look at the one-point motion and prove that it's uniformly geometrically ergodic with a unique invariant measure. This is usually the easier step. You want to prove that these dynamics are chaotic, so they have a positive, strictly positive Lyapunov exponent. And then you have to study the projective motion and the two-point motion and prove also geometric ergodicity, unique geometric ergodicity for these processes. This entails proving irreducibility, aperiodicity, and some regularity for your processes. And well, for the two-point motion, we can't really do two things. So we can't really prove it's strong Feller, and that's why we do T-chain. And we seem to need to use the double randomization of phases. So typically mixing is harder to prove than Lyapunov exponent. And also in the paper of Bedrosian, Blumenthal and Puschen-Smith, it is harder, and they need some more randomness, and that's actually reflected in this work as well. Okay, you do need to randomize two phases at each time. I mean, that's what we can do. We don't know how to prove that we can do this exponential mixing with just one randomization of phases. I should say, actually, for the complete honesty, that the Pierre-Mer model really had one randomization of phases. So that's an open question. So I'll just conclude with a couple of open questions. One is, well, I just showed you T2, and you can, play around with these techniques and construct smooth mixtures in any dimensions. You can try to reduce to the minimum the degrees of freedom, so putting less and less randomness. Okay. Yeah, that's something I think an interesting question. You can also try to put small diffusion, study Bachelor spectrum. I think the questions of intermittency can be phrased in terms of certain quantities related to Lyapunov exponents and mixing. I think it's an interesting direction to take. On the harder side is how to construct time periodic mixers in any dimension. So what we do is definitely not time periodic. This I think is very hard. And also to quantify the mixing rate and the Lyapunov exponents in terms of some parameters of the system. So, for example, the switching time. So you remember from Zlator's talk, he was saying that reducing the switching time may affect the mixing in the deterministic, may even kill the mixing. However, it doesn't seem to play a role when you have randomness, at least in our case, but maybe you want to quantify the Lyapunov exponent in terms of switching time. These are not, they're extremely hard direction, quantifying all of this. We just know that the Lyapunov exponent exists and is positive. And the mixing rate exists and it's positive, but we don't really know even how to relate the mixing rate with the Lyapunov exponent. So, and with this, I want to thank you for your attention.
Thanks a lot, Michele. And I think we have quite a bit of time for questions. So I would open the discussion. So I see Giovanni raised hand.
Hi.
So, please.
Okay. Can you hear me?
Yeah.
Yeah. Okay. So I had two curiosity actually. One, can you go back to the decay estimate, decay of correlation? Somewhere here. How do you know somehow how the alpha is connected with the S? So I guess that if S goes to 0, alpha has to go to 0. Yeah. I don't want to guess anything. So
yeah, it should go to 0, right? Because
exactly. Is there anything or that you?
No, I mean, so I know one way I can estimate exactly this for the Cracknell model. I have a simple argument that is very explicit and will give me explicit. That's the only way I know how to write down what alpha is in terms of all the parameters you like. And it is indeed true that it goes to 0 as S goes to 0, but I don't remember now what is the quantification because I don't know what to do with that thing. So I never really pursued that too much. But that's the only way I can explicitly relate alpha with S, with the Lyapunov exponent, with everything. But otherwise, I don't know how to quantify that. No.
Yeah. So in that specific case, what kind of
which flow it is?
Yeah,
it's this guy here. Is this gas and the
no. I want yeah. So the decay of alpha is roughly. I mean, what is it?
I don't remember if you're asking if it's S or S square or something.
Yeah, that's also.
Yeah, I don't know. I can check though. I have some notes and.
Okay. Perfect. Fine.
Definitely, I can check. I don't remember. Yeah.
Okay. Thank you very much.
Yeah. Thank you.
And I think we have both Lucio and Tarek. So maybe Tarek has the camera on, so I would have the video on.
Okay. Hi, Michele. So you said at the end something about time periodic. So is there any way to introduce randomness to that, or it has to be deterministic?
So the way I can introduce randomness here is two ways, basically. One can be through the tau, but this will not make it periodic if I change it every time, right?
Yeah.
And so I think it's an interesting question, for example, to see if I can choose tau instead maybe in like among 5 numbers randomly, but you know, something that they cannot go to crazies, but maybe I don't know how to do that.
Yeah.
But yeah, no, I mean, the way I write it down like this, I don't see how to make it periodic except for taking tau constant and beta constant, right?
Yeah.
Each time. So yeah. No,
Yeah, but taking it discrete, like you said, that's like a step.
Yeah, I think that would be a step forward.
Yeah.
I think that's what Andres Latos does in his simulation. He picks the phases in at least discrete set of times, or maybe it's just a countable set of times. I mean, it's a simulation, so it's going to be discrete. It's going to be a finite. But yeah, I think that's an interesting direction, actually. Yes.
Thanks.
Yeah, thank you.
Thank you. Then I think we have Lucio.
Yeah. Hi, I wanted to ask a question about one of the problems you mentioned in the end. So about higher dimensional generalization. I mean, because, okay, the sort of naive guess would be to say, okay, now I alternate n shear flows, each one to an assigned direction. At least for me, it would be the natural. I mean, what's the problem, basically? I mean, does the analysis get much more difficult? Or
well, it doesn't, but I mean, if you want to do, for example, dimension 200, right? Then you have to do, I don't know, 200 square, whatever that is.
No, okay, computation, okay, but I mean, just to say, I don't know, I can also take d equal to 3. So the other
yeah, d equal to 3. I mean, something that we're thinking about doing is just take some other, like the ABC flow, randomize it, and maybe, you know, just so that it's a nice, well-known flow. You randomize phases, and you can do it. But yeah, I mean, it's not the problem per se, in my opinion. I think it's a straightforward generalization, provided that you can check sort of these linear algebra conditions, basically.
Okay.
In
so
fact,
the Lyapunov function part doesn't create.
no, that is not dependent by the Lyapunov function. Aperiodicity is also something that you can check by computer and requires some linear algebra condition, but I think this is more expensive. So that's the most expensive one to check.
I see. Okay, thanks.
Yeah.
Thank you. So we have Michele.
Hi. Yeah, I have a question related to what you say about the dissipation. Like, if I understood correctly, a key argument for you is to discretize the PDE, right, as a random dynamical system. Now, if I want to write down the viscous case, I would add, for example, a jump process that shifts like by square root of nu with equal probability in the 4 directions. Would you be able to do that model, and the quantification that you expect is like a convergence of E log nu T, something like that?
Yeah, I mean, in fact, my result with Tarek would say log nu squared, right? With Tarek and Matthias. But it should be log nu. I agree. I mean, we haven't really thought about this because, yeah, we thought about, we were thinking more really about implicit mixing. But yeah, it should be possible to just do what you're saying, or some version of it, and extend it to the dissipative case.
Thanks.
Any more questions? Oh, Maria is there?
Michele, can you explain again if mixing is, I mean, if it's universal mixing that you obtain in this way, I mean, I got the result on the Lyapunov exponent, but can you say more?
Yeah, so it is universal because of this.
It's okay.
Basically, this tells me that, okay, it's universal up to paying some regularity on the initial datum, which is some HS regularity. So if you just put S equal 1 here, you get H minus 1 for all initial, H minus 1 uniform decay for all initial data in H1.
Okay, thanks. And alpha is who?
Alpha is some number that comes out of basically this argument here. So you can prove that, so basically the 2-point process decays by at some rate by the Harris theorem. And that rate is almost alpha. Alpha is anything below that rate that is given by the Harris theorem. So, but I don't know how to quantify. That's what I was saying. It's some rate that is positive. That's all I know. Yeah. It's related to the convergence of the 2-point process, the speed of convergence of the 2-point process.
So I think Siming is a question.
Oh, hello.
Hello.
I would like to follow up on Michele's question. So you can directly write down the semi-group estimate for dissipation equation, passive. I mean the enhanced dissipation. You can directly write down an estimate right now for the log nu to the -2.
Yes.
Okay.
So that comes out,
naturally
out of this work. So that relate mixing rates with with enhanced dissipation rates, but I think it's maybe log nu in this case, not log nu squared. So you'll be slightly suboptimal if you just apply that theorem as a black box, basically.
Thank you.
Yeah.
I had one more question.
Okay.
Is there any relation between alpha and your lambda 1, or it's?
Again, I don't know. I mean, I would say alpha is less than lambda 1 for sure.
Yeah.
So I won't have matching rates or anything like that. But I don't know how to quantify that. I mean, the only examples I know is this Cracknell model in the whole space, and I can really write down something explicit. But that's all I know. Yeah.
So Gautam has a question too, and then I would close the question time and we switch to the next talk. Hi, Gautam.
Hi, Michele. Nice to see you. Thanks.
Hi.
So I was wondering, I don't know if you remember these balance assumptions that I talked about in this paper with Tarek in my talk, right? Can you check it for these guys? Right?
No, again, because I don't know what alpha is. So I know that the Lyapunov exponent tells me that the growth in H1 is t to the lambda 1 t, right?
Right.
But I cannot say, and I doubt that you can say that alpha is equal to lambda 1. I mean, I have no idea how to say it, but that's what you would want to say, right? And
that's what we want.
Yes. Yeah. No, that would be very hard, but maybe in the Cracknell model it's possible. Yeah, I don't know. Just because that's more explicit. So I haven't checked that. But yeah, I don't know. It's a very hard question, I think. Yeah.
Thanks.
Yeah, thank you.
Great. So thanks again, Michele. And I propose we switch directly to the next speaker, Tarek Elgindi from Duke University. Is it good? Okay, fantastic. And the title of the talk of Tarek is Remarks on Enhanced Dissipation. So please.
Okay, thank you very much, Gianluca and the rest of the organizers. Thank you also to Gautam, who took my place when I was supposed to talk on Monday. Today I want to talk about enhanced dissipation. So maybe in this group it's not necessary to go back to the basics, but let me just do that. So we're starting with the looking at the advection diffusion equation. Okay, so oftentimes look at this. So we have the energy inequality. So we're on maybe the just spatially periodic solution. So we don't want to deal with boundaries or infinity. So we just look at spatially periodic solutions. And we have the energy inequality, which is just gotten by multiplying by F nu and integrating. And the conservation of the average, since the average is conserved, you can actually, I mean, we can just assume from the beginning that the average is 0. Right? And this is an assumption we'll make basically throughout the talk. Just it doesn't change anything. It's just adding a constant. And then we know by the Poincare inequality that this is less than the lambda 1, so that's the first eigenvalue times f squared, and that gives us, independent of what u is, it gives us a decay, which is the heat equation decay, like this. Okay, and so this is independent of what u does. The L2 norm is always decreasing, and it's always decreasing at least at this rate. And so enhanced dissipation, as we know, is just so enhanced dissipation. Okay, so it's the presence of the velocity field, right? So it does not change, you know. So in the inviscid case, then the L2 norm is conserved. But generally speaking, the solution goes to high frequency. So the gradient of F, the gradient of F in L2 usually will be going to infinity. Okay, and that should mean that when we use the Poincare inequality here in the previous thing, when we use the Poincare inequality, we actually made a mistake. So that the correct bound that one should do here, okay, it's kind of unnecessary, but you can write it like this. You can write F in L2 squared times the ratio F in H1 squared over F in L2 squared, right? So this is the correct, this is an equality now. And then the correct equality, the correct decay is this one. So it's the integral in time of the ratio of H1 squared divided by L2 squared. Okay, and that tells you that, and this is all, these are all nu dependent, so I always forget about that. So it tells you that the rate of decay in reality is determined by the ratio of the H1 norm to the L2 norm. And the ratio of the H1 norm to the L2 norm is like the average frequency, right? And that makes sense. If you have, for the heat equation, if you have a harmonic, so like, not a harmonic, like an eigenfunction of the Laplacian, it decays at the rate of its eigenvalue, right? And its eigenvalue is its frequency. So the rate of decay is actually given by the average frequency of the function, right? And so since the presence of the velocity field should drive this to infinity, then you should expect generic velocity field to be so-called relaxation enhancing. So we give a definition. So there are different ways to make this definition. Here's one way. So we say that U is relaxation enhancing. So we say that U is relaxation enhancing okay, so U is, but it doesn't have to be autonomous, it's just a velocity field that's C1, and okay, in order that you not make any wild statements, you should assume U is at least uniformly bounded in time with values in C1. So the Lipschitz norm of U shouldn't be growing in time or anything like that. So we say that U is relaxation enhancing if for all F0 in L2, the solution, okay, so let me state it back. If there exists a constant C0 and a function delta of nu, with delta of nu divided by nu going to infinity as nu goes to 0, so that every solution satisfies F and L2 of the viscous problem, F0 and L2 exponential of minus delta of mu t. And there should be C0. Okay, so this is a way to quantify. So this is a way to say that you get dissipation, which is faster than the normal heat equation dissipation as nu goes to 0. Okay, so this is our definition of relaxation enhancing. Okay, and so this was, of course, given in the literature that I read. So this equivalent definition was given in work of Konstantin Kiselev. Okay, I always forget how to spell Rizik's name. Okay, this is not correct, probably. And Zlatos, and this is when U is time independent, and they gave a necessary and sufficient spectral condition on U that will tell you that it's relaxation enhancing. So in 2 dimensions, when U is, or in general, when U is Hamiltonian, you don't have, it can't be relaxation enhancing. But the condition they gave is, in the time independent case, is just that the U dot grad should have no H1 eigenfunctions. Okay, and then there was also a extension given by Kiselev, Zlatos, and Kiselev, Sternberg, and Zlatos to the time independent case. To the time periodic case. So yeah. So now I want to give, just so we fix ideas of what I'm talking about. So I'd like to give the general idea is that if all solutions of the inviscid problem, mu equals 0, grow in H1, as t goes to infinity, then this should be an equivalent statement. So maybe I shouldn't add if. This should be equivalent to relaxation enhancement. Okay, so I want to make this first precise so that we understand what. So the talk is about, in what sense can you pass from H1 growth of the inviscid solution to a relaxation enhancing statement about the viscous problem, right? Okay, so you can make this precise in the following theorem. So theorem. So let U be infinity in time, C2 in space. Maybe you can relax the C2 assumption to C1, I'm not sure, but so let U be L infinity in time, C2 in space. Then U is relaxation enhancing. Oops. If and only if there exists rho going to infinity, so it's a growth function, so it should be positive and all that stuff. So I'm being kind of unclear. So rho is just a positive function that diverges in infinite S, so that for all solutions, for all H1 solutions, F to the transport equation we have the average in time, so 1 over T1 minus T0. So the reason that we have 2 times is because U is not autonomous. If U is autonomous, we just take the integral from 0 to T and put 1 over T of the gradient of F in L2 squared should be bigger than rho of T1 minus T0 F in L2 squared. F in L2 squared, of course, is a constant. It's independent of time. Okay. And in fact, we can compute a lower bound for the rate, delta of nu, in terms of rho. So if I'm not mistaken, delta of nu is just bigger than a constant nu, rho of a constant log nu. Oops, sorry. Okay, maybe I should. Maybe I'll. Okay, so we wrote the carefully. So maybe on the next slide I'll just write it slowly. Write it quickly. So if the So again, the condition is that the average H1 growth is for the inviscid problem. Oops. So if this holds for all solutions, then this is for some rho that goes to infinity. This is equivalent to U being relaxation enhancing. And it also implies so this is not sharp. It also implies that delta of nu is bigger than nu times rho of C log nu. Okay. There's a constant here, and the constant depends only on u, the C2 norm of u in L infinity at time. Okay. So in the autonomous case, it means that this growth of the H1 norm is equivalent to no H1 eigenfunction. In the pure time-dependent case, it's not clear if you can have a spectral condition at all. And so this seems to be a useful condition to have. So let me explain the proof a little bit. Also, I should mention that this came out of discussions with Gautam. So let me explain the proof a little bit. And the proof follows very closely previous work I have with Michele Coti Zelati and Mattias Delgadino. So the proof is basically so the main idea is to prove that all viscous solutions, so if F nu is a viscous solution, and let's just say that at time 0 its L2 norm is 1. If F nu is a viscous solution, then you can prove that on any time interval of size log nu, take the average of the viscous H1 squared, that's bigger than the growth rate, with a small constant. So you can put a small delta here. Delta is a universal constant, take 1/1000 or something. And C needs to be sufficiently small, depending again only on the C2 norm of U. So this would imply what you want, because you just keep repeating the argument on the whole. So if you on each log nu time scale, the average, so it means that the H1 norm on that time scale is like log nu multiplied by this extra growth factor. Then you find that you get order 1 at the total. So if this was true for every tau, so it means that you can repeat this. Then it implies that the total dissipation on a time which is much smaller than 1/nu, which is the usual heat equation dissipation time, that this is order 1. And again, T nu is a time, it's basically the inverse of this. That's not very difficult to see if you knew this. Okay, so how do you prove something like this? You just And the idea is just similar to other things. So you just approximate the viscous evolution by the inviscid one. And the key is that this is always valid. So for initial data with, say, F0 and H1 bounded by nu to some small negative power. So if F0 and H1 is already very large, then you basically won. So, you know, part of this is to prove like a contradiction argument. So you can assume that the H1 norm is initially kind of small. And you can also, in fact, assume that the H2 norm is not very large. Oops. Right, so if you assume these assumptions, and the key to this time interval C log nu, so the key to this, to breaking things up into this time interval, is that the inviscid evolution, in whatever norm you want, H1 or H2, only has a growth rate of e to the ct, right? Where c is a fixed constant. If this little c is very small, then on this time interval, you only grow by a small amount, right? And then you see that the difference between the viscous, so you have this bound, you have the L2 norm of the difference between a viscous solution and the inviscid solution. This is like the zero viscosity solution. So this is controlled by nu, the integral, sorry. So since if they have the same data, right, this is controlled by nu times the integral of the H1 squared, right? So you get closeness in L2 if nu is very small and you're working on a very short time interval, which means it's a long time interval, but it's relatively short compared to nu, then this will be nu to a small power. So this will be like nu to 0.9, because you have nu to the 1 here, and this doesn't grow very fast, right? Because of the assumption on the data and the assumption on the time interval. And then you just say that to get enhanced dissipation, you need a lower bound on the H1 norm of the viscous solution. So you just interpolate. So you just say F minus F nu. You already know that you have an assumption on the velocity that the inviscid solution grows in H1, sort of on any time interval, in an average sense, right? So it's an integral in time sense. It's not. So I should have mentioned that the reason for the integral in time in this assumption, right? So it's not true that the H1 norm always grows, right? Because you can have like unmixing, right? So you could have something that's like, if you have a shear, you may have something that's very unsheared, and then when you shear it, it goes back to size 1, right? But then when you take the time average, that's fine. It doesn't take the time average, you remove this issue of unmixing, right? And that's all you care about for enhanced dissipation is the time average. You don't care about that it's growing or decaying, right? So you just interpolate. So to show that F nu also in H1 is large, you just interpolate. Okay, and I'm a little bit sloppy about H1. So because the average is 0, H1 just means the gradient, and H2 means the second derivative, right? So we don't need the lower order terms. But okay, it doesn't matter. But so if you just say that this is nu to a small power, and on our time interval again, this doesn't grow very much, right? This doesn't grow very much. Yeah, so that's all I wanted to say about that. So then you can get that f in h1 squared, f nu in h1 squared is bigger than f in h1 squared up to a small constant, okay, minus things that are small on the time interval you chose, right? And that validates this and the so that validates this and the enhanced dissipation. Okay. So by the way, if there are any questions in the middle of the talk, I'm okay with that. So any questions about what I'm saying here? All right, so let me give an example where this is actually holds. So let me give an example. So this is, I think, a nice example to see why the integral in time is actually helping. So if you take the average 0 and x solutions, of the of this problem, so just a shear flow. Okay, so now I'm cheating a little bit because it's not going to be on the torus. It's okay. So and we assume that u prime is never 0, so it's bigger than a constant. So it's just a monotone shear flow. Then you can prove that because it's time independent, the velocity, you only need to prove this. You need to just compute the time average. So in fact, the time average for any H1 solution of the inviscid problem is bigger than a constant t squared. Okay, this is for any solution of the inviscid problem. And if you think about it, this gives you the sharp dissipation for shear flows. And okay, so it's a cute computation to show this. I guess I don't really have time, but it's really just direct, right? So you just compute, f is for a shear flow for the inviscid problem. F is just given by this formula, and you just compute the H1 norm squared, and it's true that the H1 norm itself doesn't have to grow, right? Because again, F0 could be of the form F0 could be the form f of x minus 1 million u of y. Then for time 0 up to 1 million, the H1 norm is just going down. But again, the time average is very large, right? So the time average is always always growing like t squared. So if you compute, so it's a very nice calculation to do. So you just compute, and there's a part at which, I mean, the key thing is that if you don't time average, you have something like a squared plus b squared minus 2ab is non-negative. Okay, and this inequality, you have no room in it, so you don't get any growth. So this could be 0, but somehow when you integrate in time, you get some different constants. So the 2 goes away, and you have 1/3. And in fact, now this is bigger than a constant a squared plus b squared. And that tells you that the integral in time, in fact, is always growing at that rate. So it's a nice computation to do. Okay. All right. So let me. So from this, what we get is that so generic H1 growth implies enhanced dissipation. Okay, and with a rate. Okay, and the rate, in the case I just said, the rate is balanced. So I'm going to talk about this in a second, what it means for a rate to be balanced. But then that gives you the sharp rate. But this is not really sharp. So this is so the rate I told you, which is delta of nu. So that's the enhanced dissipation exponent, is bigger than nu times rho of c log nu, where rho is the growth rate. So for example, if you have, I guess if you have positive Lyapunov exponent or whatever, like Michele was saying, this would only give you, so this cheap argument that I said would only give you an algebraic, so this would be like nu to the 1 minus C0, right? If rho was an exponential, right? But okay, we know that this is not sharp, so a sharper computation, so sharper rates can be gotten from a stronger assumption, from a mixing assumption. So you could have, perhaps, I'm not really sure how you can, in a time average sense, write down the mixing rate, but probably you can. But perhaps from a mixing assumption you can. And the key difference between this, so if you had exponential mixing, independent of how fast the other norms are growing, you would have a delta of nu is bigger than log nu. So both of these are, oh, wait a second. So this is, also log nu to the minus 2. So, right, in the case you have mixing, so exponential mixing, you can get much stronger rates than if you just had exponential growth. And there's a reason for that. The exponential growth of all solutions or whatever should not imply a logarithmic time scale, right? So, sorry, just a second. So exponential mixing should imply logarithmic timescale, but exponential growth of all solutions in H1 probably does not imply logarithmic timescale. Okay, I'm not sure about that statement, but it's unclear. But and the reason is that so H1 growth does not really mean, so it kind of means, but does not really mean that you have a lot of energy in high frequencies. Which is actually what you need for enhanced dissipation, whereas mixing does. So mixing tells you, all this is about the inviscid problem. So if you imagine if I just tell you the H1 norm of a function is very large, all of its L2 mass could be down here, and it could have very small L2 mass at a very high frequency, and that's very large in H1. But if you turned on viscosity in this, it would kill completely this piece, and you would not feel it in the L2 norm, right? The L2 norm wouldn't go down. Oh, sorry. Right. Whereas mixing implies that, there's no energy in the low frequencies, right? So it's like the opposite. Everything goes to high frequencies. So, for example, okay, this is not really a counterexample, but for example, in the cellular flow case, so cellular flow. So you take like the velocity is the perpendicular gradient of sine x sine y. Right, so it means that the flow lines look like this. Right, so just rolls in each square. Then if you were to take a perturbation and center it on this point, then the solution does grow in H1, right? You have exponential growth in H1, but it's not proven, but I think it's clear that there's no logarithmic enhanced dissipation in this case. Right, so it's likely that, you know, if the velocity is time independent, that you cannot really achieve a better delta of nu than this. Oh, maybe I should say that. Okay, this is kind of, I guess you could say it's a conjecture, that if the velocity is time independent, 2 dimensions, then you cannot have, even if you restrict to like what's called like mean zero data, mean zero on the Hamiltonian data, the enhanced dissipation rate should not be faster than u to the 1/3. Okay. All right. So that means if this is correct, it's not clear that it's correct, but if it's correct, then growth of H1 alone won't really give you the sharp rate. Okay, unless you also assume something else. So one of the reasons that I'm insisting on this growth stuff rather than the mixing is that, as you can tell, mixing is much more difficult to prove than H1 growth. So for example, if you just go to shear flows, right? If you're in the right setting, the mixing, you prove it by some stationary phase argument or something. It's a little bit involved, but for growth, you just have to compute, right? You can compute the H1 norm of the solution because you have a formula. So generally speaking, proving growth of H1 would be a better way to deduce enhanced dissipation. So if there were criteria in terms of growth of H1, it's potentially more useful than mixing criteria. Okay, so but the problem is you don't really get sharp rates from growth. But there is some cases when you can. So let me. So you can, and Gautam talked about this, but let me just mention it again. So you can have called balanced growth. So that just means that it's a type of growth that ensures that there's energy in high frequencies, right? So, and that's given by, so if you think about just a harmonic at high frequency, sorry, an eigenfunction at high frequency, if all of the energy is in one eigenfunction, it means that there's a scaling of norms, right? So the H1 norm is like lambda, H2 norm is like lambda squared, H3 norm is like lambda cubed, right? So balanced growth is just a way to say that, to generalize that. So obviously a solution of some transport equation can't just have all of its energy like, hopping along modes like that. Okay, it could happen at discrete times, but so you want something that can generalize this a little bit, and that's bounds like this. So if you have something like this, so function is growing in a balanced way if its H2 norm is growing, say, like the square of its H1 norm. And there's nothing special about H2. You could, H1 is special because we're talking about enhanced dissipation with the Laplacian, but H2 norm is just any space stronger than H1, right? So if you have, H1.5, then the exponent here should be 1.5, etc. Okay. So under this assumption, as Gautam had said in his talk, then you have that the projection to frequencies bigger than lambda, so I'll tell you what lambda is, in L2 is bigger than something like 1/2c, where lambda is just the average frequency. So remember this is precisely the thing that determines dissipation. So this determines, in the very first slide, so it determines dissipation, right? The rate of dissipation in any diffusive process is given by this, right? So if you have the energy equality, the rate of dissipation is just the integral in time of this, right? So when you say that the amount of energy higher than this is bigger than 1/2c, it tells you that, so it can tell you that you have, so if you just go, okay, so I don't want to, so the rate, the equation was something like F in L2 is bounded by F0 and L2. So this is all viscous, so I'm kind of, not being very clear, but right. So this was the decay rate we proved, right, for the viscous problem. So if you could show that for the viscous problem, you have energy like this, maybe it's like lambda squared, actually. Then you're in business. Okay. So if you have a lot of energy above lambda, then you have a good chance of proving the sharp rate. And that's indeed the case, at least on the first time interval. So the balanced growth will imply the sharp rate. Okay, so let me just quickly in the last few minutes mention some examples where you can have balanced growth. So examples. So this is the case of monotone shears. So this is that computation I mentioned at the beginning. Okay, so balanced growth only needs to be, by the way, in a time integral way. So you can formulate it in different ways. So monotone shears. Okay, so I should put in parentheses. So the sharp rate on the first first sharp. Okay, I'll tell you what that means. So it just means that the sharp rate to bring the H1 norm down by a fixed constant, right? So if you're asking, so what's the dissipation time, right? So if you're asking if you have viscosity nu, how long does it take for the H1 norm to cut in half? Okay, if you have balanced growth, you can get sharp rate on that. Right? So monotone shears, the dissipation time is like nu to the minus 1/3, right? Another kind of curious example is if you have slowly varying periodic shears. So this is I think a very interesting computation in its own right. So slowly varying periodic shear. So these are shears which have, it has a critical point, right? So it's periodic and it's smooth, but you translate it in at the correct speed so that it's balanced, right? So so I can just tell you what it is. So if you take u of y, so shear, which is cosine of y plus log of 1 plus t. Right, so cosine of y has a critical point, so you don't get the sharp lower bound for the H1 norm for data which is supported, say like that. So you say I'm going to translate the shear. If you translate it linearly or do something like that, or too fast, it's actually going to just cancel itself out and you don't get any growth. And it turns out that there's a unique function, basically, okay? It's a unique rate of growth, that rate of motion, that gives you the sharp linear growth of the H1 norm for the inviscid problem, and that's taking it logarithmic. So this is it's not non-smooth or anything, right? It's just as time goes to infinity, it becomes kind of slower and slower. Yeah, so here you can also get a dissipation time, which is nu to the minus 1/3. A third case is what Gautam talked about, is when you alternate shears. Alternate shears, okay. Alternate shears, but you have to do it in the right, you're increasing the frequency, and it's a multi-scale argument, actually. It's kind of non-trivial to do it, but you can alternate shears in such a way that it remains balanced just by, so the shears are like sine and cosine, but they have slightly different structure, and that it's straight for most of the domain, and then it transitions. So it's like a regularization of a sawtooth, right? And in that way, you can have some balanced growth. So maybe I went over my time, but I think an interesting, so interesting question. And this sort of mirrors exactly what Michele said, but it's probably easier in that enhanced dissipation might be easier than mixing. So find time periodic velocity field so that all solutions of the viscous problem, okay. So I don't need to say, oh, so that the dissipation time is like, so in fact, as far as I know, as far as time periodic mixers go, there are not many examples in 2 dimensions. So there's an example I have with Andres Latos that he spoke about a few days ago. But really, to get a smooth time periodic velocity field, so that T nu is anything, but okay, so if you want the best thing, you want the dissipation time to be logarithmic or even a power. That's okay. Okay, so I think I'll stop there.
So thanks a lot.
Thanks.
Other questions or otherwise remarks?
Do you mind give more comment about the last one? Yeah, the last line and then sawtooth one. Yeah.
Oh, this one.
Yeah, thank you. Yeah.
Right. So this is what Gautam spoke about. So, so this is. So you basically define something like sine shears. So it's like you take a regularization of sawtooth. So if S is sawtooth, epsilon means regularization, and then you make it high frequency, and J also. So you take the regularization and the frequency to 0, frequency to infinity, regularization to 0, right? Then you can make a choice of epsilon J and NJ so that the growth is balanced. So that in that setting you get anomalous dissipation, as Gautam said, but it's only coming from growth, right? You don't prove any sort of mixing is occurring, and probably there's no mixing in the usual sense. Yeah, so I could go into a little more detail about this if you want, but it's quite technical. So it's not that bad, but how you choose the regularization and the frequency is a little bit complicated.
I can check his video. Thank you.
Yeah.
Thank you. Michele has a question as well.
Yeah, thanks, Tarek, for the talk. You mentioned that you expect that nu to the -1/3 to be nu to the -1/3 to be the optimal time scale for a non-autonomous velocity field, right?
Yeah.
I'm wondering, like, if this is somehow related to what Elio Marconi presented, its result with Bonicato, that you cannot mix faster than 1/t.
Yeah, so I think it is related. It's related in that I think both results have to use something about, you know, that the hyperbolic points are not very frequent, right? I think Gianluca also has some results in this direction, right? So if you have a nice autonomous velocity field, then the hyperbolic points are not very frequent. So that's the kind of argument you'd want to use. I think it's definitely related. But of course, you know, as I tried to say, the mixing is kind of a much stronger statement than enhanced dissipation. So it should be a little harder to prove that this is the case. But I still think it's the case.
Thanks.
Camilla, do you have a question?
Thanks. Oh, can I go, or is there someone before me?
I think Matthew can go.
Okay. Okay. Hi. So I wanted to ask you. So first of all, thank you for highlighting the role of this quotient in mixing. And so this quotient you can quantify rather well without viscosity. And I want to have your opinion about the case with viscosity. So how, like, what can you do? Yeah.
Yeah, this is actually a really good question. So I should have mentioned this. So I thought about this problem a bit, and so I think when the velocity is autonomous, first of all, then probably, okay, so this is just, again, maybe unfounded statement, but this ratio, okay, no, so no, let's not. So when the velocity is autonomous, I think that this ratio should be uniformly bounded, depending on viscosity. Right? So it means that you cannot have. So if it were to grow in time, I mean, right? So the soup in time.
Mm-hmm.
If it were to grow in time, then you would have super exponential decay, right? You'd have like e to the, as t goes to infinity, it starts to really, go down. My impression is that in the autonomous case, this might be uniformly bounded. In the time even the time periodic case, it's not 100% clear to me. It would be extremely interesting to have an example where it's unbounded, I think. So I call this the lambda problem. So I guess a lot of people care about this. It's not my problem. It's a lot of people's problem. Is this what you're asking about?
Yeah, yeah, exactly. Yeah. Thank you.
Yeah, no problem.
We have Michele now in our queue.
Hi, Tarek. I was just wondering, the easiest criterion that you can think of in terms of proving enhanced dissipation is if you can prove an H minus S estimate on the viscous problem directly, right? If you have that, you have enhanced dissipation at the sharp scale.
Sure.
So why do people don't do that? I mean, once you know how to prove mixing for the inviscid problem, then okay, you sweated enough, kind of thing, and then okay, just add small viscosity just to try to prove the same thing. And it seems very hard, but do you have any, I don't know, insight?
Probably that's harder than getting an example like this. If you could have continuous mixing even with new positive, you would have this going to infinity. So it's probably probably even harder than this. And I mean, you would think that with viscosity, it should saturate at some scale, it should just stop. But that's the autonomous case. So in its time dependent, it's not that clear.
Yeah.
Yeah, I mean.
Okay, any more questions? Okay, so that's not the case. So we thank Tarek again. It's very nice and inspiring.
Thanks.
The next speaker is Siminge from Duke University, and is going to talk about applications of enhanced dissipation phenomena. So please.
So thanks, Gianluca, for the introduction and invitation. And today I'm going to talk about application of enhanced dissipation phenomena. And now these are joint work with Alexandra Kiselev and a graduate student, Yishu Gong. And now basically Yishu Gong do all the numerics in this talk. So yeah. you can appreciate some pictures here. And now the outline of the talk will be as follows. And I will first give a big overview about enhanced dissipation of shear flows. And now I want to restrict to this sub-problem of random searching of agent. And now I'll further restrict to a sub-problem of elliptic equation in the very end. So it's across different scales. And now the main object of study is the passive scalar equation. Tarek already discussed that. But then here I want to use a slightly different formulation. So it's more intuitive. So basically here, our vector field U is fixed in time. And now A is a large parameter. It's like the strength of the shear. And now if A is very large, we are stirring things very fast, okay? But basically it's equivalent to the small viscosity case, okay? So, and now for this equation, as Tarek discussed, and now it's classical to assume that the data is average 0. And now if you have shear flow, typically you want to assume that the average in the x direction is 0. And also we do some kind of subtraction. We take the x average and now remove that. And now the remaining part is called the remainder. Okay, so it captures the feature of the solution. And now if f naught is equal to 0, and now the solution get homogenized in certain direction. So if we stir a cup of coffee, and now Michele do this nice numerics together with Theodore Drivers, and now you have milk and coffee, and now you are stirring it horizontally, and now you see that they are going to homogenize very fast in the horizontal direction. So that's the basic idea about enhanced dissipation of shear flows. And now, but how to visualize this kind of phenomena? And now how to explain this phenomena? Tarek already explained to us about, okay, H1 growth create decay. And now basically that's the intuition here. Fast oscillation in space correspond to fast decay in time for heat equation. So if you have a heat equation in the T and Y variable, by separation of variables, you have two solutions. One of them, if you have slow variation in Y, it decay with rate 1. And now if you have fast oscillation in Y, it decay with rate 100. And now shear flow is a very effective tool to create oscillations, okay? So together with a transportation of shear flow and periodicity, you can just stretch the density and then wrap around the cylinder, okay? In this talk, we are considering torus, so it's just stretching, wrapping, stretching, wrapping. So in this way, you can see we have a lot of oscillation in the Y direction. So that's how you enhance dissipation. So even without the X derivative, X dissipation, you still get some enhanced dissipation. But then to visualize that, it's very simple. I have a density here. And now if I turn on the shear flow, and now the density get homogenized in the horizontal direction. And now it corresponds to the fact that the remainder F not equal decay very fast. Remember, F not equals just like the feature which are depending on X. So that's the basic idea, okay, on the physical space, okay. And now, but then I want to keep two examples in mind. Later, I'm going to use them. So for general shear flow, the first example is just a smooth sine Y flow. Jacob Bajosian and then Dongyi Wei proved this enhanced dissipation estimate. And now due to our special normalization of the equation, I will rewrite the decay rate as follows. So if you stir it with speed A, and now the L2 norm will decay with rate A to the 1/2. So basically all the F naught information will decay on time scale 1/A to the 1/2, which is extremely short. And now the heat decay is like on order 1. So that's the first example. And now next I'm going to present another flow, which is called a zigzag flow. It's somewhat considered in Colombo, Coti Zelati, and then Widmer's paper. If you have zigzag, basically the derivative is positive, is non-zero everywhere except for 2 points. And now in this case, through some resolvent estimate, you can show that this data are decaying with rate A to the 2/3, which is much larger, okay, formally. It's much larger than 8 to the half. So that's the enhancement of dissipation, okay, for zigzag flow. And now later we are going to use these two pictures. And now next I'm going to do a brief overview about the literature, but then it's long, and now I don't have enough time to explore the full glory of all the different methods to explore enhanced dissipation. And now these are only works on general shear flow. And now Michele Coti Zelati and Michele Dos also have work on enhanced dissipation for vortexes, etc. And now that's also a huge community. So people usually use Fourier analysis, hypercoercivity, stochastic method, resolvent estimate, energy estimate, and Homander vector field method to get this enhanced dissipation rate. Okay, and now basically these kind of estimates are very useful. Okay, so basically you can apply it to study the stability of fluid flow, and now there's a huge community there, and now you can use that to study plasma physics. And now there are many other subproblems like Kuramoto-Shervasinsky equation, like sampling and flocking. So basically, in 3 pictures, you can summarize some application: stability of shear flows, plasmas, or birds flying in the sky. Okay, in certain scale, you visualize this kind of enhanced dissipation phenomena. But then today I'm going to restrict myself to some applications. Okay, so it's called a random searching of agent. So basically we consider fertilization process of marine animals. So basically in the ocean, okay, marine animals will release egg and sperm into the seawater. And now once the 2 gametes meet, fertilization happens. Okay, the eggs are relatively heavy, so they are going to stay in a specific place. And now the sperm will be washed away by the seawater. Okay, so okay, you might ask, okay, if there's only sea fluid transportation, and now how come the 2 gametes can meet? So the abalone developed a nice mechanism to overcome this difficulty. So the egg of the abalone will secrete some chemicals which will attract the sperm, so that the sperm will move along the seawater. And now when they feel the chemicals, they're going to try to turn around and then meet the egg. Okay, so some marine scientists do this experiment. So you have a Taylor-Couette tank. In the interior wall, the tank rotates to the left. Exterior wall, the tank will rotate to the right. And now they are going to put the sperm into the seawater and now turn on the Taylor-Couette tank. And I'll put the egg inside the seawater for 10 minutes and then count how many of the egg are fertilized in the end. They observe some non-trivial relation between the strength of the shear and the fertilization success rate. So when the shear rate is relatively small, and now they see that, okay, the fertilization rate will increase. And now after a threshold, the fertilization rate will decrease again. So this is a non-monotonic behavior. And now motivated by this experiment, now let's take a look at the equation we are considering. But then it's just a stochastic differential equation. I'm not going to analyze this equation, okay? And now we are going to focus on some elliptic equation in the end. But then that's the setup. Basically, I have a searching agent, and now it's transported by the shear flow. And now this is a periodic domain T2. The agent are transported in a horizontal direction. It will get attracted by the chemical densities, and now it will do some random grounding motion. And now the chemical attraction will be determined by a cutoff function together with some direction of grad C. C solves an elliptic problem. Okay, it is not a passive scalar equation. And now the main object of study for us is this elliptic equation. Okay, so and now this is the basic setup. And now we want to study like success, okay? So how to quantify success of this searching agent. So this agent, you can think of that sperm, and then E is the egg density. As long as the sperm hit the egg, we call it a success, okay? Now, how efficient, so this is just a cutoff of the function here. It's not very important. And now, how to quantify the success? So we want to study the expected first sitting time. So if the time it takes for the sperm to reach the egg is less, and now we call it successful. And now we want to study the relation between the expected first sitting time and now the shear strength. And now we do a bunch of numerical simulations. And now let's think about that. Okay. So first, I'm going to present you the result. If there's no chemical attraction, just pure advection by fluid, and then that's it. And now we saw a monotonic decreasing first sitting time. So basically, it's expected because the agent are transported in the horizontal direction very fast. So you are searching in the horizontal landscape very fast. So the searching time will decrease, but there's a specific barrier to you because the agent cannot move very fast in the vertical direction. So you cannot pass certain threshold. Okay, so that's what happens if there's no chemical attraction. And now if you have chemical attraction, the picture becomes more interesting. So the yellow one is the one with pure shear attraction. The other one is just with chemotaxis. So you can see this non-monotonic behavior. First, the searching time will decrease. And now after a specific threshold, it will increase again. Okay. And now at the limit, it will approach certain things. Okay. And now it's analytically challenging to capture this optimal configuration. So, okay, I cannot do that. But then we can do something as A goes to infinity. So, and now that's the main theorem I'm going to present today, okay? Oh, sorry, okay. And now we also plot some trajectory. So basically, if the strength of the shear is relatively slow, and now you can see the agent will just approach the egg in a very slow fashion. It's just moving. And now if you have optimal configuration here, okay, the agent will be able to travel in the horizontal direction very fast. And now when it is closer to the egg, it have the ability to turn around and I'll still find the egg zone, okay? But if the shear flow is extremely strong, and now even though you are quite close to the egg, it will get washed away by the fluid stream. So that's the three configurations we saw, but then we are not able to rigorously justify this picture, okay? Now, but then we can say something about the limit. So basically, for the previous system, if the strength of the shear is strong enough, and now the expected first sitting time of 2D problem is the same as an effective one-dimensional problem. So originally, the problem might be very complicated. It's a two-dimensional. Calculating the first sitting time is hard, but then in the end, you can use a one-dimensional problem to solve that, okay? And now, solving one-dimensional problem is like solving an ODE. It's not very challenging. So, and now let me make some comment about the theorem. So if chi is equal to 0, and now basically you are considering a very trivial SDE with just horizontal shear, and now the result is a consequence of the Friedland-Wenzel theory. And now this right-hand side is explicitly computable. Now the main challenge in this limit is to show homogenization of the chemical density. And now this will give us some new insight to different equations. So let me start the last section of this talk. So basically, we want to study so let's take a look at the SDE here. It's just a randomly searching agent subject to shear flow transportation, and now we lost chemical attraction, and now some Brownian motion. So if you want to show a limit for this SDE, and now you better show a convergence of the attraction vector field. And now it happens that the C solves an elliptic equation, which have a huge shear here. Okay, it is not passive scalar. And now, so in order to derive any kind of limit, I need to get a control over this elliptic problem. Okay. Now let's take a look. We do some simulation of this equation. Okay, so you can explicitly solve that using some MATLAB, etc. So in the numerics, we see that the chemical densities will have a peak, and now you can see that it's highly concentrated near the center. So the picture is the following. I have a source, I have an exon and then you have a density there. It will secrete some chemicals. Okay, if A is equal to 0, you are just solving an Bessel equation. So it's a perfect circle, almost a perfect circle, and then the density is like that. But then if you turn on the shear, and now the chemical density get homogenized in the it gets stretched in the horizontal direction. As A goes to infinity, you might expect that, okay, it will become a one-dimensional object. It will get homogenized in the X direction, okay? And now, remember, for this equation, in order to determine the dynamics, it's not the density that it is important. It's the gradient of the density that's important. So let's take a look at the vector field generated by this equation. So the red arrow here are the chemical gradients. You can see that as A become larger, the vector field become more and more regularized. In the end, it become just pointing upward or downwards, okay? So we want to justify this convergence, okay? So let's present the main theorem here about this equation. Hopefully it can be applied in other settings as well, okay? So first of all, I have a torus, and now I have a shear flow. My target is centered at the origin, at the center, and now it secretes some chemicals here. And now the density, chemical density N are concentrated in a very small ball near the center, okay? Now, we can prove the following homogenization result. So basically, we have to decompose the solution into two parts. One is the main part, X average, and now the other is the remainder. So if you want to show that everything get homogenized in the X direction, you want to show that the remainder become very small, and now its derivative become very small. That's the main challenge here, okay? So, okay, these are the assumptions. Shear flow, assuming the target density is supported in a very refined region. And now if A goes to infinity, all these chemical gradient will go to 0 with a specific rate in terms of A. So a natural approach to attack this problem, okay, is to consider the corresponding passive scale equation. And now let A goes to infinity, and I'll try to see whether there's a convergence, etc. But then it turns out there's an easier way to do this. Okay, so that's what we want to do later. And now to simplify our analysis, I will do a L2 estimate. Okay, basically, if you want to do L infinity estimate, you lose log. And now if you want to do L2, everything will be fine. Okay, so I'm going to introduce what's called a connection formula. So there are two ingredients in this proof. One is this connection formula. The other is called the localization technique, okay? So for the chemical equation, we solve an elliptic equation, but then you can consider the corresponding evolutionary equation with initial data N. So the source in the elliptic equation correspond to the initial data for the passive scalar. So all the solution to the equation for the elliptic equation can be represented as a time integral of the solution to this evolutionary equation. If you integrate it in time, and then you get a solution. So that's the idea. And now, yeah, I happen to learn this formula in someone's final defense, okay? And now you can use this formula. Let's try to use it, and I'll try to see whether we can gain homogenization. It's very simple. So if you want to show homogenization, you want to show the remainder here is extremely small, okay? So we have a linear equation. You have this elliptic problem. By using the formula, you can see that using some enhanced dissipation estimate of non-degenerate shear flow, okay, which we do it before. It's like the Giorgi and Coti Zelati estimate. And now when you integrate an exponential function with a to the half decay rate, you bring down a to the half, and now which is much less than 1. Very good, okay. And now you can do it for the partial X derivative. So partial X derivative is also very good. But then unfortunately, this idea does not apply when you want to calculate anything like partial Y derivative. It's a classical phenomena for advection diffusion or passive scalar. When you take partial Y, because the derivative land on the Y, and now you have an extremely large source term here. And now doing this naive approach, you have A, and now A to the half, it happened to be order 1. And now all the chemical, and now if you want to do L infinity estimate of the partial y, it will be of order log A, and then which is just blow up in your face. So not helpful. But then the next idea we have is to introduce localization. So the egg happens to be localized near the center of this torus. And now it happens that, okay, this support of the initials, remember, n is like the initial data of the passive scalar. And now it happens that the density is quite far from the critical point, okay? So we can consider the following 2 equations. One is the passive scalar subject to zigzag flow, which is the blue curve here. And now the other is the passive scalar subject to a sine flow, okay? They have different enhanced dissipation estimate, as we saw before. If you have a smooth profile, the decay is a to the half. But then if you have a zigzag, and then the decay rate is a to the 2/3, okay? So they are quite different. And now, okay, basically you imagine that, okay, maybe the shear flow is not pointing upward or downward. And now if there are any justice in the world, the density, initial density here cannot propagate to this changing region. So now we can do a cheat, okay? So up to an error of size e to the minus a to the 4th, okay, basically due to this localization effect, you can translate the classical enhanced dissipation estimate here into a more effective one. So basically you can change the rate by restrict your time scale, okay? And now basically, okay, if we have time, we can explain more, but then at this point, let's assume that this decay rate holds, okay? And now I can start to do the analysis. So, okay, sorry for the long computation here, but then the basic idea is the following. I have a problem. We know that the solution is the integral of this passive scalar equation. And now we can decompose the time horizon in the short time, 0 to a to the minus a 4th, and now a to the minus a 4th to infinity. And now in the short time scale, by paying an extra exponentially small term here, you gain an effective enhanced dissipation estimate, okay? And now on the long time scale, you can do whatever enhanced dissipation you have, and now you have a very small factor here. As a result, you gain that, okay, the C0 is decaying very fast. It's like C over a to the 2/3. And now you can apply similar argument to show that the partial x derivative will behave like C over a to the 2/3, which is better than our previous estimate, okay? And now for the partial y derivative, okay, this problematic term does not go away. It is still here. And now you have an enemy A, okay? So you can decompose that into 2 parts. For the first part, you can do previous estimate. For the second part, okay, the enemy is A here, but then when you use this estimate 1 over a to the 2/3, you have 2/3 plus a half is larger than A. So you get homogenization in the partial y variable, okay? And now basically at this point, you are able to show all the convergence of chemical gradient, okay? And now after that, okay, you can use some very simple stochastic analysis technique to show convergence of the expected first sitting time, okay? So that's the main idea, but then let's summarize, okay? So in order to study elliptic problems, there are 2 ways, okay? One is study long-time behavior of passive scalar. The other is to use this connection formula, okay, we have here. Okay, there's a connection formula. Okay, connection formula we have here. But then when you estimate it, sometimes when you estimate gradient, it will not work out. And now at this time, you might want to explore more structure of the right-hand side. For example, localization, decay, etc. And now by doing that, you have a more refined estimate of the elliptic problem. And now if you want to attack a nonlinear problem, you can start from here and then upgrade this estimate, okay? So that's all I want to talk today, and thank you very much.
Thank you. And thank you very much. So are there questions? So I see Michele is raising hand.
There is first Anna, I think.
Pardon?
There is first Anna.
Anna, you want to ask something? Ask anything? No.
Okay. Yeah. So okay.
You're too shy.
Okay. So first of all, thanks a lot for the very nice talks, Ming. I really enjoyed it. As far as I understood, you don't have a quantitative rate of the first hitting time. You just know that as A goes to infinity, you will hit at some point your actual target.
Yes.
But
yes,
somehow you have a quantitative way of how the gradient should push your solution towards the target, and the shear flow gives you a quantitative rate on how fast you should homogenize in the x direction. And I know that the argument is stochastic, so maybe it's kind of difficult, but like Theo and Michele have this paper where they do the lower bound, and I think it can be applied for an upper bound. Like, have you thought of giving a quantitative rate?
Michele have a work on the, you mean the sharpness of enhanced dissipation rate, that one?
Yeah.
That's lower bound, yes, agree.
Yeah. And I think that you can use similar arguments to prove also upper bound. I'm not sure.
Yeah, that would be a very nice question. So essentially, if you prove that upper bound, it means that you use stochastic method to prove enhanced dissipation. Yes, it would be very nice.
Okay.
Yeah, but then I'm not sure. Yeah, I'm not very familiar with how do you use stochasticity to do this searching time thing, because the domain also have a small problem. Okay, so it's the domain is a circle, and then studying the first sitting time there, I find it a little bit tricky. So if you just draw two lines and then you want to study like how it approaches the strip, and then I think it's much easier. But if I have a circle and then have to do some martingale things, and I'm not sure. Yeah. So. Yeah.
Okay. Right. Thank you.
Any more questions or comments?
Okay, so now I have to ask a question. So in thinking of your physical setup, I would think that, also looking at these circular symmetric flows makes a lot of sense, right? Because you're looking at dispersal of, say, instead of a shear flow.
You mean like this? You mean the Taylor-Quinn?
Yes, exactly.
I think it works. I think there's no difficulty there.
But do you
just need to?
Yeah, go ahead.
I think you have same thing. I think you have same thing, because all this estimate you can. So basically, it relies on enhanced dissipation of shear flows, right? And now, if you have Taylor-Quinn tank, and then it's just a circular flow, and now it's in a channel. So I believe, at least, okay, so Dallas Abritton and then Beakey and then Novak claim that you can do it for channels using this method. And now I expect that you can also use resolvent estimate to derive enhanced dissipation in channel. Once everything is developed there, I don't see any difficulty in showing this result. So it doesn't really matter. So the boundary condition on the upper and lower part is not really matter. Maybe you want to worry about whether the agents hit the boundary of the Taylor-Quinn tank.
Yeah, that's what I was thinking. Yeah.
Yeah, modulo that. Yeah, modulo that. Maybe. Okay.
Okay.
Yeah, if it hits the boundary, of course, it doesn't work. Yeah.
All right. Thank you.
Yeah, thank you. Thank you for the question.
Any more questions? Okay, so we thank Simingen again.
Thank you.
Good, so I think we can start. So this is going to be the last talk of our workshop, and I'm very happy to have you here. to have in our workshop Pierre-Emmanuel Jobin from Penn State University. And this is going to be about the compactness of numerical solution to continuity equation on non-Cartesian grades. So please, Pierre-Emmanuel.
Thank you, and thank you very much for the invitation. Again, I just regret this was actually a pretty bad week on my side, and I couldn't attend as much as I would have liked. So this is a new work that we are just finishing with my graduate student, Datong Zhu. And it's really about trying to understand how we can pass to the limit in relatively basic numerical schemes for transport equations, but schemes on non-Cartesian grids. And this is creating a huge amount of problems, as I've tried to explain at the beginning. So the main object, right, during this talk will be the linear continuity equation. Right. Which, you know, simply reads something like this. At the continuous level, right? And so typically here B is given. And it's a nice it's a nice field in the sense that it belongs to some Sobolev space. And U is the unknown, so that's what you're trying to solve. Okay. And while I will focus for simplicity on the linear case in this talk, this is not our real goal, right? The goal is to handle more complicated systems and nonlinear systems. And so one example that is a little bit more interesting is when you couple this continuity equation with, for example, a Poisson equation on the velocity field B. So now B is not given anymore, but you solve it based on U. So you get to something like this, right? And then you have a Poisson equation, and B is just obtained by taking the gradient of the solution to the Poisson equation. So there's a huge literature in this kind of model. They are actually very common in certain type of settings, right? So it's a toy model for pedestrian dynamics, for example, and for other kind of flow. Down the line, what we would be really interested in, but something that we cannot do at the present, would be compressible fluid mechanics. So we'd really like to handle compressible Navier-Stokes, for example. Right? Then it's likely that I will need a lot more time before I can actually give you a result on compressible Navier-Stokes. Okay, so at the continuous level, those models are relatively well understood now, and I'm not going to go that much into this, right? This is essentially the theory of renormalized solution that plays a big role when you have velocity fields that are only Sobolev. And there are plenty of people who are expert on this. So it's another good reason to skip trying to do a 5 minutes introduction to this. What I will be interested in is the discretization. And the convergence of discretized equations to the continuum limit. And this is less understood. And I'll try to, we do have some results, I'll go over some of them, but I'll also try to explain why this is less understood. So what kind of system do we have, right? At the level of the linear advection equation, if you take an upwind discretization, you'll have something like this, right? So you take a grid, right, which, you know, might be something a little bit complicated with all sort of meshes everywhere, right? Stuff like this. Okay. And then on right, grid cell number I, well, you want to approximate U by UI, and you want to solve a system on the UI. And the system will look something like this. Right. So this is the volume of a grid, right? And then you sum over all grid points that are nearby around you. And you're going to have some sort of discretization, right, of the divergence, and so you can expect to have something like this. So this is a pretty standard upwind discretization. Here, Bij, right, is a discretization of the velocity field. And you have to discretize it over each of the facets that connects the cell I and the cell J. And Sij is, of course, the section between cell I and cell J. Okay, so the natural question, right, is what happens with this with these solutions when I'm shrinking the grid, right? So if this has a typical size, let's call it H, right? The question is what happens the limit of UI as H goes to 0. And now, what you can remark relatively immediately is that if you have reasonable assumptions on the grid and you have reasonable assumptions on the discretization of B, right, passing to the weak limit in the equation is not so hard. Because in particular, if the divergence of B is bounded, then you will propagate LP norms of U, discrete LP norms, and uniformly in the grid size, you will pass to the limit. With natural assumption. Okay, fair enough. Now, if we were just interested in the linear equation down the line, right? This might be good enough. You might still want to have some sort of strong convergence for numerical purposes, but at least this would give the main result. The issue here is if I want to go to a system like this, right? I need strong convergence. I need strong convergence to pass to the limit in the Poisson equation. No matter how you're going to discretize it, you will need to pass to the limit in G of UI. And this is why I want compactness. Right. Very well. What can we do? Right. I said that we already have some results. So what do we know? What can we do for all of this? There are essentially two branches of results that we understand relatively well. First of all, we understand reasonably well the case where B is Lipschitz, which is not a very big surprise. All right, and there's quite quite a bit of a large literature on this, so I'm not really going to go that much into the details, right? For Navier-Stokes, Galouet and Herbin worked a lot on that. So you can see, I mean, there's a huge series of results that you can look at. There's also still on fluids. There's a recent paper by Goudon, Lobel, and Manjot. And in general, you also have some result by Merlet and Vauvel that are a little bit older. And certainly many others. I'm not, again, I apologize, I'm not going to cite everyone. And this is for any grid. The other case that is relatively well understood is Cartesian grids. And the reason Cartesian grid is better understood, I'll give you a very trivial example in 2 minutes, and you'll see the problem with non-Cartesian grids. Cartesian grids mimic rather well what is happening at the continuum level. And so there you have very explicit regularity estimates, for example, by size and schlichting and size. Try not to misspell that. And we also had a paper using a different method with Ben Belgassem. And again, I should mention Galouet et Herbin, who have a lot of things. De la Rue Lagoutière is another very nice result with discontinuous coefficients. Lagoutière-Vauchelet, sorry. And again, and so forth. So, all right. The big question is what happens when B is not Lipschitz, which is our case, because actually, even with Poisson, right, even if G is bounded, so the Laplacian of phi is infinity, but that's the best you can have, and so that won't give you a Lipschitz B. Could be log Lipschitz, but then you might lose more when doing the discretization as well. So what happens if B is only W1P, right? With P not infinity? And what happens if the grid is non-Cartesian? And you might want very easily to have a non-Cartesian grid in things like that, because specifically you might want to discretize more in the regions where B is more singular. And there we know very, very little. But we still know something, and there's one case that is still relatively straightforward, and it's to prove compactness by using the uniqueness of a limit. Now, this forces you to be in the linear case. So you can obtain compactness from the uniqueness of a limit. Through a standard argument of renormalized solution that, I'm again going to bypass. And Boyer in particular has several papers that, and also Guillaume Boyer. The issue is, to do this, you need the compactness of divergence of B. All right, and I'm going to put commas here, right? So you need to define a discretized divergence for the Bij, and you need to have a compactness of that. And that's because to have compactness in a continuity equation, you need the compactness of B, and you need the compactness of divergence of B, right? And this just comes from the formula on the characteristics, where you see that the divergence of B shows up, and that's because I have the equation in conservative form. And so the problem here is, in the nonlinear case, the divergence of B is connected to U. Right? If I go back to my example with Poisson, divergence of B is Laplacian of phi minus Laplacian of phi, actually. So, for example, divergence of B is exactly G of U. And so now you would enter into a circular argument. You will need the compactness of divergence of B, but then this requires to prove the compactness of U, but then this requires the compactness of U itself. And you're stuck. And so this is a very good example of a case where instead of having some abstract compactness, what you would really like to have is some measure of regularity, because then you can bootstrap it and the argument becomes very easy. Okay. And this is exactly where the non-Cartesian grid interacts in a very nasty manner with singular beads. And let me give you an example of a non-Cartesian grid, a trivial example where everything can be calculated, where we start from a constant B, and you will see some of the problems. All right. So let's do 2D, right? Let's do 2D, and let's do a very trivial equation where B is constant and parallel to the first axis of coordinate. Okay. And let me do the following grid. Okay, and of course, just giving a sample, right? Then you can extend it. So 1 row out of 2, I am going to have cells that are half the size in the horizontal direction. All right. Now, this is an equation that when you discretize it is going to be posed row by row. So what you have is a 1D discretization in each row, except with a different size. And then you glue together all the solutions. It's super easy. What is the regularity of a numerical solution? Well, it's not BV, for example. In fact, you can calculate it, right? So again, not very hard, and you see that it is in WS1 for all S strictly less than 1/2. If you're looking for Sobolev regularity, that's essentially the best you can do here. Again, trivial calculations, right? Very interesting because we start from a constant velocity field. If I had a Cartesian grid, there wouldn't be anything to that at all. But because I have a non-Cartesian grid, everything behaves as if the velocity field actually was not constant and was quite singular. If I start from a non-constant velocity field, things are even worse because I have no idea how that will interact with this kind of crazy discretization. So that's the issue, and it means that in some regards, this problem is quite a bit more complicated than the analysis at the continuum level. So what could we do here, right? So previously with Bendel-Gassem at the continuum level, I had the idea of introducing a kernel to measure regularity. Right, and so what that meant essentially is we were considering semi-norms of this type. Right, plus some discretization at epsilon. And the key was to have here exactly the critical singularity from the Calderon-Zingmunt point of view, right? So the dimension. And you see that this, if you had zero regularity on mu, because it's just not integrable, right? That would behave in log of 1 over epsilon. And so you can build semi-norms by imposing that it behaves slightly better than log of 1 over epsilon, right? And whenever you will have a bound on any of those, right, that is going to imply compactness, and that is going to give you some sort of log derivative on the solution. Right. And this also proved very useful in mixing. If you push the estimates much further than what we had done, so there's actually a lot of work there, and I'm going to refer to this very nice paper by Seeger, Smart, and Street. And the paper by Lazier after that uses this result to explain exactly what's the best what's the best amount of derivatives that you can get and all of this. Okay, so I would like to do the same thing here. Okay, in the discrete case. So fair enough, right? So let me define this kernel KH, right, which is going to be something like that, like what I wrote above, right? Just with a phi with compact support to avoid the tail at infinity. That's not really the issue. The issue is the singularity of k near the origin, right? And now what I'm going to do is for any points x tilde I, right? So to each cell I will assign a point. And once I've done that, I can build a seminorm, right? A discrete seminorm just as before. And so this will look something like this. Now, I don't want to push too much, right? So I don't want H to become comparable with the discrete size of the grid. So I'm going to impose a lower bound here. And then I don't want it to become too large either. And then you'll have this 1/log H, right? I'm sorry, it's not H, it should be epsilon. Let's adopt epsilon, 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 and then I will do the sum, right, over all I and j over the grid of okay epsilon of xi tilde minus xj tilde, right, and ui minus uj. And here I will put the volume of each cell, which now will denote pi. That's this volume. That's the volume of cell I. Okay. So that is the natural extension. Can I propagate those seminorms? This turns out to be a very fun and non-trivial question. Because it depends on the choice of the xi tilde. So, for example, right, our first idea, of course, was to take the xi tilde equal xi, the center of the cell, right? Now, you can take, instead of xi, you can take another point within the cell. In general, in that case, I have no idea how to propagate that seminorm. So we were rather pessimistic with all of this, right? And so what can we actually do? And let me state here a first result. Assume the grid is periodic or almost periodic. So this is a very special case. Obviously, it doesn't cover all Cartesian grid. It doesn't cover the most interesting Cartesian grid. Although the almost periodic case, and I'm not going to describe what I mean by almost periodic, is getting close to having a lot of interesting grid. So by periodic, what I mean it's not necessarily Cartesian, but you have a pattern, and you have a pattern with a finite number of cells that is periodized, and that's what gives you the grid. So you have this pattern right? And then you periodize it. You need good assumptions on B, so you need good assumptions on the discretization. That is not a big surprise. Right, so you need to reasonably preserve the Sobolev estimates and things like that. If you don't do something crazy, that is going to be satisfied. Then there exists point xi tilde that are not so far from the center. Right. They might not lie within the cell, though. They might be away, that might be a little bit further away, but not crazily far away. And then this semi-norm is propagated. So that the sequence of UI, right, is compact. For example, if you define a function that is piecewise equal to each UI in the corresponding cell, then the corresponding function has some uniform regularity and is compact. All right, and let me give a very brief idea of what's going on here. If you're careful and you're writing the corresponding commutator estimate when trying to propagate these semi-norms, you realize that what happens is you need a particular algebraic relation on the xi tilde. To get an equivalent of the commutator estimate at the continuum level. And this is the relation that that you need. Right. So if I'm looking at all the neighbors of I, sorry, it's GI actually. And again, I have this Sij. And this needs to be equal to some B tilde I, but you may define as you want, which here is typically going to be the average of B over the cell, but it could be something else. Pi I. And again, pi I is the volume. And if you want to do almost periodic, or you want to have something a little bit more general, you can also add a remainder here, a plus Ri pi I, as long as the remainder, of course, goes strongly to 0 in L1 at least.
Dear Manuel, quick question.
Yes.
So when you have a commutator, so it's because you're commuting, I mean, you're regularizing at some point here?
Yes, so this is right. So if you look at that, right, and you do d of dt of this, you have exactly the same type of commutator term as when you take a convolution in the standard Fourier renormalized solution.
Okay.
Right?
Okay.
So you go to the discrete level, you'll find something like that with a lot of extra terms that you have no idea how to handle. Unless you have that. And what's interesting is this is actually, this is a diffusion equation. It's a non-self-adjoint diffusion equation on the grid. Right? Or non-symmetric diffusion equation on the grid. And the question now becomes, how do I get estimates that are uniform in the grid size for solution to such a non-diffusion equation? For what matters, how do I even get existence, right? And so far, this is something that we are only capable of doing when the grid is periodic or almost periodic. That's where the limitation comes from. But it might be that there is a way to extend, I don't know, some of the non-symmetric degenerate elliptic estimates, right? Alexandros Beckelman-Pucci, for example, maybe has an extension at that level that could help. This is something I don't know. Better understanding this equation is the key to going to more general grid. But as far as I know, this had never been written on the numerical side. So it's a nice, very natural, very nice looking equation that shows up. And so that's what we are hoping to do now is getting better estimates on this equation to be able to handle much more general case. But of course, to go to Navier-Stokes with this, for example, what you will need is do something like what we have do with Bresch, which is adding weights, and that I have no idea how to do yet. All right, I will stop here. Thank you very much.
Thank you very much. So that was very nice. And we still have quite a bit of time for questions. So I would just open the discussion.
Or I can talk more if you want to see the calculations.
Let's see. In fact, I would have a question. So if I understand correctly, so but tell me if I'm wrong. So in a sense, you are considering, at least for the linear case, independently the vector field or its regularity and the grid.
Yes.
And then you try to prove estimates or solves uniformly in the grid. Well, I think that what people in numerics do, so they try to resolve with better grids in the places where the vector field or the solution, they are the most irregular. So
Yes.
would this simplify things? So in a sense, you could take the good grids once you have the vector
No,
field.
it makes it
It's
even
more
worse.
simplifying.
Yeah. Yeah.
Why worse?
Because you complicate the topology of the grid. What happens here is what you're solving is you're really solving a system of cohomologies on a graph. Like you should think of it like that. And if you have a Cartesian grid, the topology of a graph is extremely simple. And it fits very well with the topology of RD. And so most of what you are usually able of doing on RD, you can do on your graph. Now, whenever you get out of that, you break this parallel. And even though you might say, well, but I'm only refining in the region, so I should keep something reasonable, it's not clear at all. Because of course, everything is coupled. So what you do in the region affects what's happening everywhere else. When you're doing the commutator estimate, you cannot easily separate one region from another.
But you could pick the grid in a sense.
Yeah, so
design a grid, but
that's why the almost periodic works. What we can actually do is we can have big blocks, right? And then you do a periodic grid in each block. Not necessarily Cartesian, periodic, and then it works. Right, so instead of stupidly periodizing this pattern, I could periodize it for a while and then I could change the pattern. Right, and that would work. So you could have something that, you know, instead of that, would look like, well, I have a nice Cartesian grid, right? And then here I have a certain size. And here I'm expecting that I have a much more singular right? And then I have a smaller size. That's good. That I can do.
Okay.
As long as this is big enough, right? And I'm not going to write down precisely. I mean, we try to quantify this as much as possible in the paper. So we have relations for that, right?
Okay, I see.
So that may be good enough for numerical purposes. It still does not allow you to refine things just as you want. And if you have a very heterogeneous situation and you want to do a complicated grid, right, with triangles, a little bit of different shape at different places and things like that, I have no idea what is going on then.
Okay, thank you.
So following up on Gianluca, so you don't need a uniform bounds on the grid size or the quality.
We do write it with a uniform bound at the present for simplicity.
Yeah, because that's what I see, but that wouldn't match your picture that you just.
That wouldn't completely. Well, we could relax that to some degree. That's clear with the present proof. So
you could have like more sparse grid in some areas and a more
Yeah.
That's interesting.
This is not a major objection, as a matter of fact, as long again as you don't try to change that from one cell to the next. Right? So as long as you stay within this sort of framework where you have relatively large regions, you could do something different in one region from the other.
So you couldn't handle anything where the grid moves, for example?
No.
Okay. Because you can't have overlaps of the...
We could have a bit of overlap, but nothing major. There could be a bit of a fuzzy region here, but it would have to remain small with respect to the size of a region again.
Yeah, that makes sense. Thanks.
Yeah. Again, it all boils down to what you can say about this equation, as a matter of fact.
Yeah.
And well, we've not been very good so far. Even though what I should maybe say is even in finite dimensions, so even on periodic case where we end up studying it on one pattern, right? It's non-trivial. And it's very non-trivial also because what happens when the velocity field is parallel to one of the facets on the grid. Right. Then the diffusion degenerates. And how do you get estimates that are uniform into those degenerate coefficients? Even if you only have a finite number of equations here, it's non-trivial.
Yeah.
Question. At least in the case that you're managing, and if you try, can you also discretize in time? Because from what?
Yeah. With the same constraints.
With the same constraint. Okay.
Don't change it too often, right?
Okay. Yeah. Of course. And the propagation works well also. Okay.
Yeah.
Thanks.
Very good. Any more questions from the audience for Pierre-Emmanuel? I don't see.
Plus, it is getting late,
Any raised hands? So yeah, here in Europe, it's already very dark.
Yeah.
But it's only 6 p.m. in fact. So
it's winter.
It's the end of a long week.
Yeah, and it's the end of a long week.
Again.
Thank you.
So thanks a lot. And well, more in general from my side, thank you to all the speakers of today and all the speakers of the week. And I see myself twice. It's been for me, very nice. So I enjoyed very much the talks and the discussions after the talks. Unfortunately, we had no discussion in Pisa, and so we'll try to, to get another chance at some point and to organize something else when the situation will allow that, which we all hope it's going to be rather soon. So thanks again for participating and interacting, and well, I hope that I will be able to see you soon in person, and all the best.
Thank you, and on behalf of all the speakers, let's thank again all the organizers.
I would say that Gianluca did a big chunk of the work, so he should get.
So double thanks to Gianluca.
And I think it's also another good occasion to thank everybody at Centro de Giorgi. So I see that Sabrina, so maybe you can switch your video on if you're around. And yeah, so she disappeared, it seems. There she is. Hi. So we thank you again for all the help. As I was saying at the beginning, organizing first something in person, then hybrid, and then online is like organizing 2 or 3 events. So the last one is easier, but yeah, there was already quite a bit of budgeting and reserving and thinking what to do for the restaurants, so for the coffee breaks and whatever in the first months in which we were discussing about that. So thanks again for taking care of all this.
And let's plan to have a follow-up in person, maybe in a couple of years or something.
Let's do that earlier than that.
Yes, I hope that in the future it will be possible to welcome all the participants in person in the Centro de Giorgi. Yeah, I hope it.
Let's hope. Let's hope it's going to be soon, I guess. Or I hope. I don't know. I don't know if I guess. Good. Then thank you, everybody, and take care. And see you soon.
Thanks again. Have a nice weekend to everybody.
Thank you. You too.
Bye-bye.
Bye.
Bye bye
Bye,
to
everybody.
everyone.
Bye.